Okay, let's get started. So, how's the test?
It was so hard. How do you write this? Like,
I love torturing people. That's why.
I could see that.
No. So I'll try to get the test graded back by Tuesday next week. If at absolute latest Wednesday of next week, so you have some time to look at it before the final. I've only graded like 6 or something, so this may or may not hold true for everyone else, but the grades are slightly lower for everyone so far from midterm 1, but it may or may not be true in general. If it is lower, I may shift them up to be closer to what you got from midterm 1. I'll have to see what the end result is, but that's what I'm seeing so far. The number one thing that you should pay attention to is if you didn't read the directions for midterm 1, you should have read them for midterm 2, because quite a few people just didn't read the directions on midterm 2. Like, for example, the question about the true-false, like the same one that was on midterm 1, but I had on midterm 2 where you wrote true or false and then the explanation for why. The directions are exactly the same as midterm 1. If you just write true or just write false, you're not going to get any points. Okay? The directions are there to help you. They're not there to hurt you. For the CNF conversion one, when you had the CFG convert to CNF, and then the other part of the directions was for each of the steps explain why we can do this in general. If you don't put an explanation there, how many points do you think you're going to get for those? None. Okay? Read the directions. They're there to help you. Okay? I was going to go over the solutions, but one, I'm not done with them yet. And two, I'd rather hand them back. I'd rather go over them when I hand the test back so you can go over your test in tandem when I'm going over the solutions. So instead of having to go back later, do it at the same time. So I'll show off the solutions on Tuesday then, or whenever I hand them back. Any questions about the test though? Or anything else in general? Oh, one thing I forgot to mention. Homework 3s are up here, so if you're one of the 4 people who turned in homework 3, your homework's up here. But yeah.
I have a question. Are we going to have the final is on Wednesday, right?
Yeah.
Are we going to have a review session that Tuesday?
Yes. So what I'm planning to do is do whatever we're going to do today and tomorrow. Then next week is only Tuesday and Wednesday because Thursday is off due to America Day. And so we're going to finish up everything we're going to do within those 2 days. And then the following Tuesday is going to be review. Entirely review, and then Wednesday is the final. So I'm sure none of you have taken my class before, but the way that I do reviews is I like doing a Q&A style session because I clearly don't know what you guys are having trouble with. So, but you guys know exactly what things you're struggling with. So like what parts of the material you're having trouble with, if there is anything you want to go over again. So here's what I want you to do. I want you to do this. So several days before the actual review session, send me an email or something. Don't send a snap to me or send me a Facebook message or anything. I'll only accept emails here. Send me an email saying, I want you to do an example with pumping lemma for CFLs, or I want you to go over question 2 of midterm 2 again, because I wasn't exactly sure what the right way of approaching it is. So tell me what things you're having trouble with, and then I'll take the collective responses and then try to tailor it to you as much as I can. Yeah.
You come to like office hours?
No, this is the review session the day before the final. Yeah, so before the final, yeah. And I will have office hours on that Wednesday before the final too.
But not just the review session, but in general, if there was like someone on the test that we wanted to like know a little bit more detail info.
I didn't hear any of that.
We can come to your office hours and like have problems done, like just do some problems with you. Like, if you wanted to,
Yeah, that's what office hours are for. That's what I've been doing with the people who've been coming. Yeah. Yeah, so that's what I want you to do for the final review. A few days before, send me an email, and don't send it like within 2 hours of the review session, because I might not be able to accommodate that. What usually happens is that either 0 or 1 person sends me an email. So what I do then in those cases is I just ask the class, what things are you having trouble with? And if no one asks or needs help on anything, what do you think I'm going to do? Go home. Okay? So I want you to maximize your utilization of me, because I want to help you as much as I can, but I don't know what things you're having trouble with. You know that. So I want you to tell me. Okay? Does that make sense? I'll mention this again down the line. But any other questions about the final or anything? Yeah.
So is the majority of the final going to be on the newer stuff?
Oh, good question. So the way that I like doing finals is that I used to have the focus of the content being the last part of the class and lesser on stuff earlier in the class. The problem with that is that students have more trouble with the later stuff than the earlier stuff. So what I think would be more fair to you guys and you would like more is to have the test be uniform across everything. So this is not true, but if we did say a third on regular languages, third on context-free, and third after that, then the final should be about a third regular, about third context-free, about third everything else. Okay? I try to make it as uniform as I can. Other questions? Yeah.
So you said that students typically do worse on the finals. Is that because of the newer content, or is there another reason?
So the reason for that, why students usually do worse on my finals, is that I used to have them be multiple choice or true false, and students do worse on multiple choice true false on my test than everything else. So that's why. But I'm planning to not have it be multiple choice true false because you do better on when it's not those questions. Other questions? Yeah.
So is the final grade going to be out like within a week after the final?
Yeah, so the problem is that I'm leaving the day after the final and going all the way to the Czech Republic. So I am taking the test with me, but I won't be returning for a long time after that, so I'll try to grade on the plane over. So the test itself, I'm planning on making it shorter in length, but the questions maybe involve a little bit more thinking. So fewer questions, but a little more thinking. And less true-false type questions, yeah. Other questions? Okay, so what have we been talking about before we were so rudely interrupted by some midterm? Yeah, ADFA, yeah. So, I don't know what happened there. I don't know why it's erasing. That's weird. Oh. Wow, that's weird. I've never seen that before. In the 3 years I've had this thing, I've never seen that happen. Interesting. So we've been talking about these problems. EDFA, then we did ACFG, APDA, ECFG, etc. We also did EQDFA, etc. So what are these things? Structurally, what are they? Are they strings? Are they sets? Are they languages? Or what? They're not Turing machines.
Languages of it.
The languages of encodings of machines. Yeah. So we encode the machine and string in the case of the A things. We encode the machine or whatever as a string, and these things are just sets of strings depending on whether the machine accepts the string or the machine has empty language or etc. And what did we see about all of them? What was the common thing that we found among all of them? They were decidable. Yep. So what was mentioned before, that there's a Turing machine. Here, decidable means that there is a Turing machine that has these languages that always halts. So like in the case of ADFA, there's a Turing machine that takes in a DFA and a given input string and checks whether or not the DFA accepts that string in a finite amount of time. It decides that language. In the case of, say, EQ DFA, therefore, because it's decidable, there's a machine that takes two different DFAs and decides in a finite amount of time whether or not these two DFAs have the same language or not. And we did product construction type stuff with that. For ACFG, it's basically the same language, but we have a context-free grammar and a string, and we want to know whether the grammar actually generates that string or not. In the case of ECFG, for example, we were given a single grammar, no string, and we wanted to check whether or not the grammar accepts nothing or not. Okay, so what about, we're not going to actually dive into this. We'll return to it maybe later. What about EQCFG? So how did we do EQDFA? Well, what we did was we had these two, this Venn diagram, and if we have the language of the machine being one circle and the other language being the other circle, then we wanted to check whether these two shaded regions are both empty. And if the first language is L1, the second is L2, then we wanted to check that L1 intersection L2 complement is empty, and L2 intersection L1 complement is also empty. Why could we do this for regular languages with DFAs? Yeah, closed under intersection and complement. What about context-free? They're not. So they're not actually they're not closed under intersection and complement. But does that show that EQCFG is undecidable? This one approach doesn't work, therefore no approaches work. More people should say no. No, that doesn't work, because just because one idea doesn't work doesn't mean another one doesn't work. It turns out that EQCFG is undecidable, but we need more technology to actually prove that. But so just to get you to think about, could we adapt one strategy for DFAs that worked for CFGs? And the answer is not always. Sometimes it can be, but in this case, it can't be. Okay, so what about E sub PDA? We're not going to dive into that either. What about emptiness problem for PDAs? Is that decidable? So if the problem for emptiness for context-free grammars is decidable, is the one for PDA decidable? Yeah, why? Yeah, just convert the PDA back to a CFG, call the decider for ECFG, and you're done. Sweet. So ePDA we can add to our list. And then we can invent other problems too. But let's just stick to those for now because I want to actually move on. unless there are questions about these. Okay, so we did regular languages. Everything turned out to be decidable. We did some problems with context-free grammars and PDAs. Some of them were decidable. We couldn't prove the answer for one of them, EQCFG in this case. What is the next level up? Has the same initials as trademark. Turing machines. So those are the levels that we looked at. Regular languages, then we did context-free, and then now we need to look at Turing machines. And the first problem we considered for the regular and the context-free case is the acceptance problem. We get a machine and some input, and we want to determine whether or not the machine says yes on that input. So let's look at that corresponding problem for Turing machines then. So ATM is machine and input as before, where M is a Turing machine, and M accepts W. Okay, and we would want to determine whether or not this language is decidable or not. Because the A problems for DFAs and CFGs and I guess PDAs, all of them were decidable. Maybe this one is too. It might be. But let's do a preliminary result. So we're not going to get to the decidable yet. Let's just get recognizable. So let's just show immediately that ATM is recognizable. So what does recognizable mean? It halts on what strings?
Strings are in language.
Right. So it halts on the strings in the language. So if we're going to build a machine that takes a Turing machine and a string as input, we want to halt if the machine we're given accepts the input. So what is a strategy that you might try? Well, how about let's just run the machine we're given on the input. If the machine actually does accept the input at some point, does that take a finite amount of time with the Turing machine? Yeah, it takes a finite number of steps. Well, suppose that the Turing machine we're given does not accept the input. Either it outright rejects it, or it just runs forever. Do we care for recognizable? Well, if we have a machine, a Turing machine, and an input that it does not accept, is it in this language? No. So do we care if it halts or not? No, we don't care. So in fact, we can get a recognizer really quickly here. So here's how we do it then. So on input MW, so we're presented the Turing machine and the string as before, where M is a Turing machine and W a string. Well, let's just run the machine that we're given on W. Well, three things can happen. It either outright accepts it at some point, it outright rejects it at some point, or it just runs forever. So if the machine that we're given does in fact accept W at some point, then we accept. And in fact, that's the whole machine. So let's see. So actually, we should be a little bit more precise, I guess, for the outright reject case. We can't really do anything about the it runs forever case, because then we'll just be stuck in step one anyway, because it just runs forever. Well, if it outright rejects W, then we should obviously reject because it's not in the ATM language in this case. So if it outright accepts it, then it must be an ATM because that's the qualification to be an ATM. If it outright rejects it, then it's definitely not an ATM because it doesn't accept the string. Well, if it runs forever, then we're stuck in step 1 and we never accept anyway. So we're fine. So we only hold on the strings that are in the language. That's the only thing that we need to do. So in fact, it is recognizable because we can't guarantee that the machine won't run forever. Okay? Why was that not an issue with PDAs? Because PDAs can run forever. I'm not tricking you there. PDAs can run forever because we could have a loop of transitions that just have a bunch of epsilon transitions on them that push things onto the stack and then pop them back off. Push them on, pop them back off. So a PDA could run forever. Why was that not an issue? Well, one thing is we can convert it to a CFG, and the problem was definitely decidable with CFGs. But if you actually think about this a little further, convert the CFG into CNF, into Chomsky normal form, then convert the CNF grammar back into a PDA. It turns out that that PDA cannot run forever, no matter what, which is pretty interesting. So it turns out you can avoid the issue with PDAs. With Turing machines, it's a lot harder because with a PDA, you're not overwriting where the input is. And so with a PDA, you could accept when you're done reading the input. With a Turing machine, you're messing up the input potentially. And so therefore, there's not such a clear definition of when you're going to accept, whereas a PDA is much clearer. So it seems like the ATM problem is considerably harder. It definitely is recognizable though, because we can just run the given machine on the input that it supposedly is given and just keep going on the simulation until maybe it accepts, at which point we should accept. Any questions on that? Okay, but let's actually prove something really important here. And that is that ATM is undecidable. Oh, and here's a quick obvious proof that that is correct. This one method didn't work, therefore it's not decidable. The Turing machine can run forever, therefore there's no way to check in a finite amount of time whether it accepts the input or not. Is that a valid argument? No, and you shouldn't accept that as a valid argument. Just because one way doesn't work doesn't mean another way won't. But it turns out there's no way that works. And that's what we're going to prove here. Okay, so prepare to have your minds blown. So I'm not going to skate around the fact that this proof is kind of mind your warpy. So it's kind of, it warps your mind quite a bit. So the way that we're going to actually prove this is, so let's give a high level idea first and then we'll get to the actual details. So the idea here is we're going to assume by contradiction that there is a decider for ATM. So that this claim is totally bogus and that there is a decider for ATM. Okay? Then what we'll do is we'll build a machine using that supposed decider and we'll just build a machine based off of that. And what will happen is that machine will prove cannot possibly exist. It's based only on the assumption that a supposed decider for ATM exists. But because this machine that we just built doesn't exist, the supposed decider cannot exist. And so it's undecidable. Okay? Another high-level argument is, well, let's look back at the machine we just built right here. So notice the last two parts where if M accepts W, then we accept. If M rejects W, then reject. Could I swap the accept and reject? I may get a different language as a result, but could I just swap those? Yeah. So here is the brilliant idea behind the proof of why ATM is undecidable. We can have Turing machines that disagree with themselves, which is pretty interesting. You can build a machine that takes a machine as input and have that machine disagree with itself, the one that you just built. And so, how many of you have heard of Cantor's diagonalization argument? This is something that should have appeared in 243. So, it may be interesting to do that. So, what is the relationship between the integers and the real numbers? This is just for the diagonalization argument, not related to the proof. But what is the relation between the integers and the real numbers? Are there more of them, or are they the same number?
Subset.
Well, they're subset definitely, but are there strictly more real numbers than integers, or is there a bijection between the two? That there are more real numbers. So there are more real numbers than integers. And what was the idea? Well, if we suppose by contradiction that there is exactly the same number. So for every integer, there's a corresponding real number, okay, and vice versa. So what you can do is then, let's actually list out the real numbers. So this is just as an example. Let's pick 405.96230, etc. And then we'll pick 2.1386, etc. And let's do one more. 6,789.8675, yeah, etc. And let's just list out the real numbers this way. And because there's a correspondence between the real numbers and the integers, then there's a first real number, say this 405 one, then there's a second one, then there's a third one, then there's a fourth one, there's a list of them. And so if I can actually make a real number that I can guarantee is not on this list, then does that invalidate my claim that they're the same number? If this is a complete list and I make a number that's not on the list, then does that invalidate the claim that they're the same number? Yeah. So here's what you do. Let's actually look at a diagonal this way, diagonal of these numbers. And I'm going to look at a digit out of each one. So let's look at this digit, this digit, this digit, and then continue all the way down. And I'm going to manufacture a number that is definitely not on this list. Here's what you do. You take, this is just an example, pick the digit in the red circles and add 1 to it. So if it was a 5, I'm going to make a 6 here. If it was a 1, make it a 2. If it was a 6, make it a 7. If it was a 9, make it a 0. If it was a 0, make it a 1, and then etc. Could this number in blue be equal to any of the numbers in the list? No, because it differs by at least one position to every other number in the list. And so because we're doing a diagonal slice here of all of the integers, of all the numbers that are listed. So therefore, there are more real numbers than integers. We're going to actually do that exact same idea, but in disguise for showing that ATM is undecidable. We're going to manufacture a machine that will always disagree with itself on some input. So there must be a contradiction somewhere. It can't get the right answer every single time. It must get the answer wrong at least once. And so therefore it can't be a decider. So that's what we're going to do. Are there any questions about any of that before we get into the details? Okay, so let's prove that this is undecidable. So, proof. And if I'm going too fast, this is probably the hardest proof in the entire class. So if I'm going too fast or you want me to explain something again, definitely ask. So let's just do our idea. Suppose that it is decidable, and let's give it a name, the decider itself, the machine that does supposedly decide this language. So let's suppose that H, I'm going to call the machine H, decides ATM. So the claim is that H does not exist. There's no decider for this language. But I'm just supposing that there is one. And then what should we get at the very bottom of this proof at some point? A contradiction of some kind. And a contradiction, namely about the existence of this supposed decider H. If we can, yeah, go ahead.
Sorry, what's the H?
Yeah, it's just the name of the decider. It's the name of the Turing machine that supposedly decides this language. I'm sticking to the notation in the Sipser book to make it as consistent as possible. Yeah, so we're just supposing some machine, and I'm calling it H because we're going to be using it. And so what is the, so let's actually review. What does decides mean here? What does it actually mean to decide a language? That you always halt, yeah. So, but also the fact that you always get the right answer. So if the answer is destined to be accept, like you're really supposed to accept the input, you will accept at some point. If the answer is no, you shouldn't accept the input at some point, you will reject at some point. You will get the right answer every single time. So let's actually write that out explicitly. So if we consider H like a function, I guess, where H takes a Turing machine and an input here, I'm going to move this over a little bit so I have some room. Well, because H is a decider, it must always halt. That means it's either going to say accept or it's going to say reject at some point. Any questions about why that's true? Okay, so the output of this machine running on this input is either it's going to say accept or it's going to say reject. So it's going to say accept if the machine that we're given actually does accept the input. If it really does accept the input, then this machine supposedly says accept at some point. And then it says reject in any other case. So namely, if the machine we're given does run forever, it never stops, then this supposed decider H can figure that out and can say reject in a finite amount of time for us. Okay? Does that make sense? One person nodded, so therefore everyone nodded, right? Does that make sense? Okay. Okay, so that's just the definition of what H being a decider actually means. So what was our idea for this proof? Our idea was, let's make a machine that uses H in some way and disagrees with itself in some way. So let's build a machine. So I'm going to build the following machine. And I'm going to call it D. So D, obviously standing for my last name, is the machine that we're going to build. And I called it D, namely because that's what Sipser calls it, but also because we'll see that this is in fact a decider for some language. It's a decider, it always halts. So let's actually make this machine. So there's no reason for this machine to exist other than to get us the contradiction. So there's no higher level purpose of this machine other than to get us a contradiction at some point. So what does this machine do? So it takes a single machine and that's it as input. So I should say where the machine's a Turing machine. So it just gets a single machine, no input here, okay? And that's actually crucial. There's no input to the machine here. No input to the machine M here. The machine D, it just gets a single Turing machine and nothing else at all. Okay, so what does this machine do? Well, if I want to use H, this machine H that we're supposed to exist, I gotta feed it a machine and an input to that machine, right? That I gotta feed the machine and an input to this supposed decider H. Well, I have a Turing machine here, but we don't have an input to that Turing machine. Well, let's do this. We're going to run this supposed decider H on, well, we gotta give it two things. I'm going to feed it the machine M and the actual string of the machine M. So I'm going to feed it its own description. Pretty weird, huh? So what the hell's going on? So what we're doing here is we got to use the decider H in some way. Well, we're only given a machine M here. So we gotta find a manufactured string in some way. So why not just use the actual machine itself that we're given? Yeah.
So isn't this kind of a circular argument?
Yeah. It's not a circular argument. It's a diagonalization argument as we're going to do. So that leads to what I was going to say next, which is why are we doing this? The reason is we want the machine D to disagree with itself. So what we're going to do eventually is we're going to feed D, this machine we're building D, its own description as input. Because D says, I can take any Turing machine as input. So let's run it on its own description because it's a Turing machine. So just feed it itself. But then we'll have it disagree with itself because we're going to output the opposite here. So what is the second step? Whatever, technical term by the way, whatever the output of H is, we will output the opposite. Yeah.
Just for simple, what's the second M? What is it?
Yeah.
Is it like a string?
Yeah, so angle bracket M, always remember, means a string. So the thing that we're feeding H is an encoding of the original machine and the string of that machine itself.
So is it like that?
Yeah, it's the correspond. Yeah, I should write that. So it's the corresponding to the string W. So normally we would feed a machine and a given string. Here we're just feeding the actual source code of the machine to itself. So how many of you have ever heard of a quine? Quine. It's a program that, like an actual computer program that outputs itself. So you run it and it outputs the exact same string. So it's the same kind of idea here. Instead of outputting the corresponding string of the source code, we're feeding the source code into itself. Yeah, go ahead.
Sorry.
Go ahead.
So here, when you say that is the description corresponding to W, that means that that's the encoding of M with
Yeah.
W as an input.
So
or
So the H machine is going to receive an encoding of an entire machine and the actual source code of the machine.
no input?
The input to the machine M is its own source code.
No, I just got confused when you say corresponding to W.
Yeah. Corresponding to W, I should say in the language description. Yeah, that's what I meant to say. Thank you.
So what's the point of feeding the actual source code?
What's that?
What's the point of feeding like the actual source code to the machine?
Yeah, so the key here is that we're outputting the opposite. So what happens, what we're going to do is we're going to have D run its own source code, which means that if we output the opposite, that must have meant that it accepted its own source code, but we outputted the opposite, which means it rejected. So we'll get to that. We'll get to that. So think about like your compiler, for instance. Could you, say a Java compiler, could you feed the code of the Java compiler into the Java compiler itself?
Yes.
Yeah, so that's exactly what we're doing here. We're feeding the source code of the Turing machine into the Turing machine itself. That's all we're doing, really.
Putting the Turing machine inside of the Turing.
The source code as a string and feeding it through the actual machine itself.
Okay.
Yeah, so again, don't read too much into this other than the fact we're just making this machine. Yeah, we're going to see. But mainly to get the contradiction. If we didn't output the opposite, we couldn't get a contradiction. Yeah, so the only purpose of this machine is to get us a contradiction. There's no higher level purpose of why this machine is being built here. But here's the thing. Is D a decider for whatever language it has? Ignore whatever language it is. Is it a decider? Does it always halt? Yeah, because step 1, by assumption, always halts, because H is a decider. And step 2, of course, takes a finite amount of time too. So therefore, D is a decider. D is a decider. Well, let's see. What does a decider mean? It always halts, and does it ever get the answer wrong? No. So let's do the same idea that we did for H before, just spelling out what decider means, for D instead. And it actually will lead us into the contradiction. So what does D take? It takes just a single machine and nothing else, remember? It takes just the machine and no input to that machine, just the machine itself. Well, because it's a decider, again, it must say accept or reject at some point. It can never run forever. So those are the two possibilities. Well, let's see. Let's look at the accept case. How did D say accept? What happened? Well, go ahead.
I'm sorry, you ran H.
Yeah, it ran H, and then what did it do? It outputted the opposite. So if the D machine says accept, what did the H machine say? Reject. Okay, so the H machine said reject. Well, what is the language of H? It's supposedly the ATM language. So what does that mean about M with its own description? Does it accept its own description, or does it not accept it? It does not accept it because H said reject, meaning M did not accept its own source code. So D will say accept if the machine that we're given does not accept its own description, because we outputted the opposite. This is not the actual contradiction yet. And what about the reject case? So if the D machine said reject, what did the H machine say? Accept. Well, what does that mean about M with its own source code? Did it accept it or did it not accept it? It accepted it. Because the answer is the opposite. So if M accepts its own description, its own encoding. Okay? So this is just spelling out what decider actually means for D. Any questions on this? Yeah, go ahead.
How would a machine not accept this own source?
That's why it's a contradiction. It's just a normal string. It could accept or not accept it, based on however the machine's actually built. The contradiction that we're going to get will come next, which is the diagonalization part. So remember, the diagonalization argument is we're going to build. In this case, we built a number that disagreed with every other number. Here, we're going to build a machine that disagrees with itself. So that means it doesn't behave like any other machine. So because it's a decider, does it have to do this correct answer and run in a finite amount of time business for every input? Yes. It has to do it for every machine it could ever possibly be given because it's a decider. So let's run it on its own description. Because it's a Turing machine, it should get us the right answer if we feed it itself. So let's look at D on its own description. Now here's where the contradiction is going to come. Because D is a decider, we can do this. It supposedly will get us the right answer. But if it doesn't, then D is not a decider. So what is the answer here? Well, it must be accept or it must be reject for the exact same reasons as before. Well, I don't know about you. Well, I think I can substitute the D for M in the 2 lines above. Wherever the M appears, I just substitute the D in. So except if D does not accept its own description. And then the reject case is reject if D accepts its own description. All we're doing is we're just looking at a particular machine. Instead of just an arbitrary machine we can given, we're just looking at a specific one. And it should get us the right answer. And it should not have any problems getting the right answer. Well, what happened here? Let's look at the top line. It said D accepts its own description, because that's what it means. It accepts it if D does not accept its own description. Can that happen? Could it accept it if it doesn't? No, that's a contradiction. Oh, okay, let's look at the other line. It rejects its own description if it accepts it. Ooh, that looks like a contradiction to me. Well, so therefore, D is not a decider. Because it got the answer wrong on at least one machine. Okay? So it contradicts the fact that it's a decider. Oh, wait a minute. We concluded above that it was. So there must be a contradiction somewhere else. Well, let's see. How was the D machine actually built? What was the only thing that we relied upon in order to build this machine D? H. So the only reason we were able to build D was the existence of H. If H doesn't exist, we can't build D. So what can you conclude then about the existence of H? Could it exist? No, because if it did, then we can build this machine D, which has a contradiction to exist. And so therefore, for this reason, H cannot exist. Oh, wait, what is H? as a last wrap up before we take a break? It's the decider for ATM. Wait, so therefore, could there exist a decider for ATM? No. So therefore, ATM is undecidable. I'll let you settle that for a few minutes, and then we'll talk more about it after the break.